In our previous video, we explored how models separate classes using decision boundaries. Now, let's dive into what actually defines those boundaries. Model parameters. In machine learning, models are intelligent systems designed to learn from data. They take an input, process it, and then produce a specific output, like a prediction or classification. But how does a model actually learn or adapt to new information and improve its performance? It does this by adjusting internal, flexible components that help the model understand patterns. These crucial adjustable components are what we call model parameters, the focus of our discussion. Continuing our discussion, model parameters are the internal variables that a model adjusts during the learning process itself. You can think of them as the knobs and dials on a complex machine. Adjusting these parameters changes how a model processes data and makes predictions. These values are learned directly from the training data, allowing the model to adapt and generalize. They are distinct from hyperparameters, which are settings you choose before training begins. Let's make this concrete with a simple linear model, a foundational concept. Consider the equation of a line, y equals m times x plus b. Here, m represents the slope of the line, and b represents the y-intercept. In our model, m and b are the parameters, the adjustable knobs that determine the line's position and tilt. By changing these values, we can draw any straight line, allowing our model to fit various data patterns. Building on our linear model, let's see parameters in action as we fit data. Imagine we have a set of data points, and our goal is to find a line that best represents their trend. Initially, our line, controlled by m and b, might not fit the data well. Through the learning process, the model iteratively adjusts and b. Watch as the line dynamically shifts, rotating and translating to minimize the distance to the data points. This continuous adjustment of parameters is precisely how the model learns the underlying relationship. Moving beyond simple lines, parameters are also crucial for classification tasks. Here, our goal is to categorize data into distinct groups, like separating two types of cells. The model's task is to find a decision boundaries, a line or surface that cleanly divides these classes. This boundary is not fixed. Its position and orientation are shaped and moved by the model's internal parameters. These parameters are instrumental in defining precisely where one category ends and another begins. In classification, parameters are often called weights and biases, especially in neural networks. Weights determine the importance of each input feature, while biases act as an offset. Visually, changing a weight might rotate the decision boundary, making it more sensitive to certain features. Changing a bias, however, shifts the entire boundary without changing its orientation. Both weights and biases are dynamically adjusted during training to find the optimal decision boundary for classification. When a model learns, it's essentially finding the best values for its parameters. This process often involves an optimization algorithm, like stochastic gradient descent, or SGD. SGD iteratively tweaks the parameters, evaluating model performance and calculating necessary adjustments. It updates the weights and biases, driving them towards values that minimize errors and maximize accuracy. This continuous feedback loop effectively teaches the model to perform its task with precision. To summarize, model parameters are the internal adjustable components that enable a model to learn from data. They are the knobs and dials that define a model's specific behavior, from linear regression to neural networks. Their values are learned directly from the data during training, allowing the model to adapt and generalize. This allows models to make accurate predictions or classifications on new, unseen examples. Understanding parameters is fundamental to grasping how machine learning models truly work and achieve their remarkable capabilities. Thank you for watching. Please like and subscribe for more.